Okay, we're going to solve some circuits now. At this point, you should be pretty good at adding resistors in various combinations to get that total resistance. So if you're not good at that, I suggest you stop here and go back and brush up on that because you really do need that skill for all of these circuits. This particular worksheet is titled Circuit Worksheet 2. It's been assigned, so you should see a blank copy on Canvas and also the answer key, but we're going to walk through each of these circuits and see how to solve them. Okay, so typically in these, the first thing I'm going to look at is the resistance. So here I've got all three resistors. So this is a 6 ohm, this is 4 ohm, and 2 ohm. Okay, so the first thing that jumps out at me is these this 4 and the 2 are in series, so I can add them in series, so I get a total of 6 ohms right here for that entire branch. And then I've got 6 ohms parallel with 6 ohms, so when I add those in parallel using the 1 over R equals 1 over 6 plus 1 over 6, we should get a total resistance of 3 ohms for that whole circuit. All right, once we have that, I'm always, this table helps a lot on the test. You may not have a table. You might want to sketch one out. But whenever I see I have two of the three things, VI and R, I can always get the third. I'm going to do that right away because odds are that's going to help me solve the rest of the circuit. So remember Ohm's law. So I've got a total of 6 volts. And then the current is unknown. I'll call that IT. And then the total resistance is 3 ohms. So then that total current is 2 amps. It's kind of weird equal sign. So then I have 2 amps here. Now what that means, the total current is the current going through the battery. So 2 amps is my current there. Alright, now if we keep looking at current, we know current 2 amps goes through here, hits this junction. Some of that current will go this way, some will go this way. I don't necessarily know how it's going to split up, so I'm kind of stuck on current. Although in this one, since I have 6 ohms here and 6 ohms here, it's going to be an even split. But let's suppose it was not an even split. We don't know how it's split up, so we're kind of stuck on current. So then we're going to look at voltage. Okay, to look at voltage, we're going to use Kirchhoff's loop rule for that, if you remember that. So I'm going to use a couple different colors here. Let's go red for an inner loop. So one loop is going to take this route. Okay, and then if I look at that loop, I know I have to lose all my voltage throughout that single loop. Well, the battery gives me 6 volts. I should write that somewhere in here. 6 volts. And then the charges that take this path, they have to lose all 6 volts by the time they get back to the battery. So this is a pretty easy one. There's only one resistor. So I start out with 6, that's what the battery gave me, and I'm going to call that V1 because it's labeled R1, and then that's the only resistor that these charges are going through. I have to end up with 0. So we can clearly see here that V1, the voltage drop across resistor 1 is going to be 6 volts. Okay, now here I can do V equals IR. I'm going to stick with the red, I guess. So I've got 6 volts equals the current through R1 times the resistance, 6 ohms. So then I've got a current of 1 amp. Alright. I can stick with the voltage or I can look at current. It doesn't matter. In fact, why don't I go to current here? So I'm going to go back to black. Okay, so, or maybe I'll switch a different color. Blue. Okay, so if we look at current, we've got the current going into a junction has to equal the current leaving the junction. So I've got 2 amps right here. I know this is 1 amp, and then I'll just call this I2. Okay, so the current going into a junction, which is 2, has to equal the current leaving the junction, which is 1 plus I2. So there we see I2 must be 1 amp. Now, if you remember, current does not do anything unless it hits a junction. So if I have 1 amp here, I've got 1 amp here, I've got 1 amp here. All right, so that all is 1 amp. Can do V equals IR on these. I'll get 4 volts there, and I'll get 2 volts here. Now, notice 4 volts, 2 volts, 4 plus 2 equals 6. So we could have done another loop for that. We would see that that all works. So let's just go ahead and get the power here. So power, you've got the 3 power equations, IV, I squared R, and V squared over R. It's a squared, I'm running out of space. Any equation you like will get the power here. So I'm not going to go through those, but you should get 6 watts there, 4 watts, 2 watts, and I'm going to calculate total power going across 12. And then you just want to double check for power. Do these add up to the total? 6 plus 4 plus 2, that is 12. I've done this circuit correctly. All right, let's move on to the next one. Okay, so here again, I'm going to look at these 2 resistors are in parallel. 1 and 2 are not in series. 1 and 3 are not in series because there's a junction between them. 2 and 3 are in parallel, so I can add those in parallel. I believe I get 3.43 ohms. And then that 3.43 is in series with R1, giving me a total resistance of 7.43. Okay, now I've got resistance, I've got total voltage, so I know I can get the current there. V equals IR. So 15 equals I total times R, which is the 7.43. So I total is 2.02. Looks like there's some rounding things going on here. So 2.02 amps. And again, that's going right through here. Okay, now if you notice, there's no junction between the battery and R1. So what is the current in R1? That's right, 2.02 amps. Okay, and then for R1, we can get that voltage drop because we know those 2 things. So V1 equals 2.02 is the current, and then 4 is the resistance. So V1, we've got 8.08. Should put units on all these. Okay. All right. At this point, we're a little stuck because the current, the 2.02 amps hits here. Some will go this way, some will go this way. Is it 1.01 and 1.01? It looks like it will not be that. Okay, never assume that. We're kind of stuck on the current, so I'm going to look at voltage. All right, so I'm going to go back. I'll use red for an inner loop. So there's one loop. And then for my outer loop, we'll use blue again. Get the Cubs colors in here. Okay. So for the red loop, all right, I know you have to lose all the voltage as charges go through that loop. So I start with the total voltage, the battery is 15, minus V1, which is 8.08. We just solved for that. And then the next thing that goes through is V2. And then that's it. So we have to be out of our voltage at that point. So that equals 0. All right. So then V2 ends up being 6.92. Okay. You can use V equals IR here. Then our current should be 1.15. I'm not going to show all that work. It's just going through Ohm's law equation to get that. And then for the third one, you know, again, we could use the junction rule because we know how much current is here. We know how much is going this way. The rest is going to go that way. But I'm going to go back to the loop rule. I'll use the blue loop. All right, I apologize. I'm going to write it in here because I'm running out of space. So for the blue loop, we start with 15 volts. That's the battery voltage. We lose voltage across R1. That is 8.08. And then we lose some across R3. I'll call that V3. And then we're down to 0. So V3 ends up being the same thing as V2, 6.92. And then we can get that current 0.865. Okay, so you should see the current right here, 2.02, and then we've got 1.15 amps here and 0.865 amps there. That should all obey the junction rule. You can double check my math there. We solved for the voltages using the loop rule, so that should be good as well. Notice you're never going to rely on the voltage adding up to the total, or the current adding up to the total, or even the resistors adding up to the total. The only thing you can count on is the power. So I'm going to encourage you to solve for all these powers. So here, again, any of the power equations of 16.3 watts, 7.96 watts, 5.99 watts, and then again, even the total I'm going to solve going across 30.3. Double check. Do these three individual powers add up to the total? If you're really close, now we rounded some numbers in here, so we might not be exact, but I think we're really close, so we are good. Okay, so let's get one more in. I'm going to be running low on time here. Okay, so this one, I see R2 and R3 are in parallel. I'm probably going to add those first. I get 1.71 ohms, and then that's going to be in series with R1 and R4, so I can get a total resistance of 8.71. Okay, V equals IR. I can get that total current 1.38 amps, which means going through the battery 1.38 amps. All right, there's no junction between the battery and R1, or no junction between the battery and R4. So all the current throughout this whole branch is going to be the same, 1.38 amps. So I know 1.38 and I know 1.38. V equals IR to get these voltages. So 2.75 and looks like 6.9 for that one. Okay, now if we're looking at current, 1.38 amps hits here, some goes this way, some goes this way. I don't know how it splits, so I'm going to have to use the loop rule. All right, so we'll go to, I like red, apparently. All right, so there's one loop. And then for the other loop, let's go green. Let's imagine it's Christmas time. It's not quite Christmas green there, but okay, so looking at the two loops, since I'm on green right now, I'll do that one. Our total voltage from the battery is 12, and then we lose voltage through R1 in the amount of 2.75, and then we're going to lose voltage through R3, or that should be V3, sorry. There's my little button here. Okay, so V3, and then we're going to go through R4, which we know that's another 6.9. And we should be down to 0 volts going through that loop. So if we solve for that voltage, we get V3 is about 2.35 volts. Ohm's law, V equals IR, gives us a current here of 0.59 amps. Okay, we can look at the other loop, the red loop. We start with 12 volts. That's what the battery gives us. We lose 2.75 in R1. We're going to lose some in R2. And then we lose 6.9 in R3. And we should be down to 0. So that also is 2.35 volts. That shouldn't be a surprise. If you remember, voltage drops across resistors in parallel, they should be the same. Okay, so we can get the current here, 0.78. Look at the junctions. Does the current in here equal the current leaving here? It should. The current going into this junction, does that equal the current leaving that junction? It should. We'll solve for all the powers. Okay, so we should get 3.8 watts here, 1.8, 1.4, 9.5, 16.6. Double check, do all these individual powers add up to the total? We're pretty close, so we should be in good shape there. Alright, how are we doing on time? Okay, so we're out of time here. I'm going to stop this video and then I'll make a part 2 and try to finish the rest of these.